طيب بسم الله الرحمن الرحيم. So as I have discussed with Dr. Ayman, you have gone through the introductory part, which covers an overview of the layered model, the TCP/IP layered model, and you have discussed the basic functionality of each layer in that model. So starting today, we are going to start with chapter 3 in the textbook, in the Frozen textbook. And this chapter talks about data and signals. As we all know, data is our means to represent information. So in real life, for any application, whether this application is health or oil and gas or anything, you need to represent information which might be like temperature, pressure, might be banking information, things like that. You need to represent this using data, right? Why do we need to talk about signals? Because we cannot send data directly on the physical medium. So our physical media, whether it's a cable or even wireless, they don't deal with actual data, they deal with signals. So a signal then is a representation, a physical representation of the data on the physical medium. Okay? So this chapter discusses the relationship between data, how we represent data, and how we represent signals, and what are the main characteristics of each one. What are the characteristics of the data? What are the characteristics of the signals? Okay? To start, whether data or signals, there are two types of data or signals. There are the analog data or analog signal, and there are digital data or digital signal. So analog and digital, they apply to both data and signals. Okay, so analog means that the data or the signal would have a continuous value, or its value changes over time, like changes over from one instance of time to another. Okay, digital data or digital signal talks about the fact that the data or the signal takes actual discrete values, finite set of values over time. What does that mean? This means that if we can measure, for example, the temperature over time, okay? So assuming that we have temperature over time, so we need to measure this temperature continuously. So I measure the temperature now, and it's like, for example, 25. But after 1 second or after half a second, it might change. Okay? So maybe... No, network. So maybe at time 0, it would start with something like this, and maybe it doesn't change, but maybe it changes later, and it goes down, and maybe it goes up and down, and so on. Okay? So this is a continuous signal, and it takes any arbitrary values over time. Okay? So the temperature can change in a flexible way. We don't have any control. Digital data talks about the fact that the actual value that the signal or data takes is finite, which means that it can have specific set of values. So it can have like a value of 1. Like if we were to measure an integer number, measure any environmental phenomena that takes an integer number. For example, we need to measure the number of the number of people in this room. So the number of people in the room cannot take a value of 1.1, 1.2, 1.3, right? So it can take 1, and then maybe after some time it takes 2, and maybe it takes 3, and maybe it drops again to 0, right? So this is what we call a digital signal, because it takes finite set of states or values, okay, within a period of time. ماشي؟ طيب فطبعا there are many characteristics of analog signal, analog data, digital signal, digital data that we will so data can be analog or digital. Analog data are continuous and they take continuous values, as we have discussed. Digital data have discrete states. By state here I mean a value. By state I mean value. Signals can be analog or digital. And as we have mentioned, signals are the physical representation of data on the physical medium. So analog signals can have an infinite number of values. Okay, which is the temperature example that we have just shown. In a range, what does that mean? Like in a small range, it can take any value. In a very small range, like if we cut a small range, it can take any value within that range. But discrete or digital data, if we have a range of time, we'll find like 1 or 2 values only. Okay. In data communications, we commonly use periodic analog signals and non-periodic digital signals. What does that mean? This means that in actual physical medium, we usually use periodic signal, and we will talk about what periodic signal means to represent the actual data on the physical medium. Why? Because the periodic signals, a periodic signal has very small bandwidth in nature. Okay, so take that as is for now, and we will elaborate on that in 1 minute. Okay, so that's why in communications we very commonly use the periodic signals, okay, to represent the data on physical media, and we usually use non-periodic digital signals. Why on the digital signal we use non-periodic? Because as we will see later, digital signal, once we say the word digital, this means that the frequency components of that signal is infinite. In terms of bandwidth, it has infinite bandwidth. It has very, very wide bandwidth anyway. So whether it's periodic or non-periodic, it has infinite components of frequency that we have to deal with. And that's why, in order to represent the digital data on actual medium, we usually use analog signals. And we will see how, we will see why we need to do that. So that's a very simple example of a non-periodic analog signal. Okay, so this is an example of a non-periodic analog signal. It can take any value within a specific range. So if we have any specific range, we see that the values change infinitesimally, which means that from one instance of time to another, the value changes. Okay? This is an example of a non-periodic digital signal. Non-periodic means that it does not have one pattern which repeats. That's what the word periodic means. Periodic means that it has one period like this, and it repeats all the time. But of course, This is not the case for this signal, and that's why we call it a non-periodic signal. Because it has finite set of values, we call it digital signal. Because it does not have repeated pattern, we call it non-periodic digital signal. Okay? So we will now talk about the characteristics of each of these. Particularly in the analog signal, as we said, we commonly deal with periodic signals because it's easier in terms of representation, in terms of devices that can generate analog signals. You can have any actual signal generators that can generate periodic signals easily. Why? Because the bandwidth of these signals is usually very small. Okay? So it's easier to deal with, and that's why it's commonly discussed and used in communication systems. Okay? And then we will talk about the characteristics of the digital signals, and usually when we talk about digital signals, we talk about non-periodic digital signals because this is the actual representation of data. Data takes, yes, even if it takes finite values, but these values in practice do not necessarily repeat. Do not necessarily repeat over time, which means that in nature, the digital signal or the digital data are aperiodic or non-periodic, okay? Because they pattern. Okay, so the periodic analog signals can be classified as simple or composite. So what does that mean? So simple means it's like similar to a sine wave. So if you have a sine wave like this, so this is a sine wave. Okay, it's obviously periodic. Why? Because it has one cycle, and this cycle repeats all the time. And it's analog because it takes different values at different time. So this is obviously a periodic analog signal. Why we call it simple? Because this is the simplest periodic analog signal that you can have, that you can generate using any device. So what is the difference between this and a composite periodic signal? A composite periodic signal takes it has pattern, but you can actually like similar, like for example, sine square, sine x square. So sine x square is something like this. So it's a square of this. Okay. Okay. So this is a periodic analog signal. This is a periodic analog signal because it has, again, a cycle, and the cycle repeats, right? Why we call this composite? Because in actual life, what we will discuss later is that we can represent this composite signal using multiple simple periodic signals. Multiple. Okay? So sine wave and cosine wave are the simplest way of, or the simplest periodic signals you can have. Any other periodic signal like this, or another example, a signal like this. Again, this is a periodic analog signal, right? So we will discuss later how we can use multiple sine waves and cosine waves, okay, to represent this composite signal. So the sine and cosine waves are the simplest representation of a periodic signal that you can have. In fact, when we start discussing the frequency components of a signal, you will realize that the sine wave has one frequency component in the frequency domain. It has only one frequency component. Any composite signal like these, they have multiple frequency components in the frequency domain. So another definition of a simple analog signal is that it has one frequency component in the frequency domain. Although we have not talked about frequency representation now, we will talk about it later, but this is just to give you a heads up. Okay? But composite signals are signals that we can represent using multiple simple analog periodic signals. Okay? But the simple analog periodic signal is the simplest representation we can use. We cannot actually use any signals to represent it. It actually represents itself. Any confusion or any question in that regard? Okay. Okay. So a periodic. Now we will discuss the periodic analog signals and what are the characteristics of these periodic analog signals. Okay. So first, this is an example of a simple analog periodic signal, which is the sine wave. Okay. The analog periodic signal or any signal can be, or any periodic signal, sorry, can be represented using three things. Okay. The amplitude. So this is the amplitude. So this is the peak amplitude. Peak amplitude meaning that this is the maximum amplitude that the signal takes in any point in time. Okay. And the period, which is the actual cycle duration. So the cycle duration, the peak amplitude, and the phase. The phase is actually the offset that the signal takes to start the first value. In that case, for a sine wave, it starts from 0, and it actually starts at 0. So we call that the phase here is 0, which means that if we want to have, for example, a sine wave which has an offset, we can do it like this. So this does not start from 0. So it's as if you have part of the cycle offset to the left. Okay? We call that this is shifted, and in that case, the phase of this sine wave is not 0. Okay? So these are the three main values that represent a sine wave in general. An example of a sine wave is actually the AC power in our houses, right? So the AC in our houses, the outlets, they actually generate an electric signal, okay, which we commonly use some values for. And we know that in the States, for example, they have 110. صح؟ اللي هو voltage level is 110. And here in the Middle East, we usually use 220, right? So this is actually this is supposed to be the peak. So when we say 110 or 220, what we refer to is actually supposedly the peak of the signal. Okay? This peak of the signal is proportional to the amount of energy that the signal takes, amount of energy that this signal carries. So if this amplitude increases, this means that the signal has more energy. If this value is reduced, this means that this signal has less energy. In practice, the numbers that we use are not in fact represented by the peak value of the signal. They use what we call the root mean square value of the signal. So the root mean square value of the AC sine wave that gets generated from the output power is 110 in the States, and it's actually 220 here in the Middle East. So what is the meaning of root mean square value? So for that particular example, we use the root mean square value to use these numbers here, 110 and 220. From the name, root mean square. So we start from the end. So first we square the signal. Then we take the mean of the signal. And then we take the square root. As simple as that. Okay. So for a sine wave, first we square the sine wave, and we have done that before, so it would be something like this. Right? Then we take the mean of this, or the average. Okay? So the peak value, itself, we square it, and then we take the average. It turns out that the average for the square sine wave is the peak value divided by 2.
No, so this is done to lower the error in choosing the peak?
No. This is different. The root mean square value is a value or a parameter which is commonly used to represent the voltage level of any signal. Okay, this is different from the mean square error, because in communication we use sometimes the term mean square error, but this is to represent something else. Here it's called root mean square value. And what that means is that we first square the signal, we take the average, and it turns out for the sine wave, the average of the square signal is the peak value over 2. And then we take the square root. So this is called the R. So this is called the RMS. So this is the RMS value, which is basically the peak value divided by square root of 2. That's it. So from that example, if I need to know the peak value of the voltage level in the US, what do I need to do? This is the RMS value. What do I need to do? Multiply it by square root of 2. تمام? So multiplied by square root of 2, you get the actual peak value of the voltage level in the US. Same here, it would be again square root of 2 multiplied by 220. Okay? So the RMS value, it turns out the RMS value is not one of the fundamental characteristics of the signal. As we have said, the fundamental parameters of the signal are the peak amplitude, the cycle duration, and the phase. So these are two examples of two signals. The difference, as you can observe here, the difference is actually only in the peak amplitude. Okay, so they have pretty much the same cycle. So they kind of synchronize. So they have the same cycle. And they both start from 0, which means that the phase for both of them is 0, right? The only difference is the peak amplitude. So what does that mean in practice? This means that this signal carries more energy than this signal. Why? Because the peak amplitude here is more, which means that the energy that this signal carries is more compared to this signal. So that's what we use this peak value for. We use the peak value to know the amount of energy that this signal carries. Okay? One parameter. So the voltage of a battery is constant. We refer to the voltage level as 220 or 110. But in fact, the voltage signal is actually a sine wave. It's an analog periodic signal. It's not fixed. It's not constant. But we use one number to represent this, which is for power, as we said, we use the RMS value or the root mean square value. Okay? The other thing is, or the other fundamental parameter is what we call the cycle duration or the frequency, and those are used interchangeably. The cycle duration and the frequency are actually one thing, but they are represented using different values. So if the frequency of a signal is 1 over the cycle duration, as simple as that. So a frequency of a sine wave is 1 over the cycle duration of that sine wave. Okay? Parameter, and for the same example, for the exact same example, we have two signals here. As you can notice here is that the difference between those two signals is not anymore the amplitude. The difference is in the cycle duration itself. Okay? So the period here is 1 over 12 seconds. Here it is 1 over 6 seconds. So what does that mean? This means that this signal changes faster than this signal. Or in other words, the frequency of this signal is higher compared to this signal. Right? So if the cycle duration is low, this means the frequency of the signal is high. Why? Because they are inversely proportional, right? Frequency is 1 over the cycle duration. So if the cycle duration is less, the frequency is high. Okay? And frequency, just as a note, the frequency has some meaning here for a sine wave. Why? Because again, the sine wave is a simple analog periodic signal. And it has only one frequency, which is 1 over t. But if I ask you, for example, what is the frequency of that signal? In fact, this signal has more than one frequency. Okay? So we cannot say that the frequency of this signal is actually 1 over t, and that's it. Because this is a composite analog signal, and it has more than one frequency. And we will see how to deal with this. Okay? So, just as a simple, very simple exercise, how to convert from the time domain to the frequency domain. And this is valid only for a periodic simple analog signal, of course, because as we said, this does not have actual meaning for the case of composite signals or digital signals or something like that. So a simple sine wave which has a duration of 1 second, this is equivalent to 1 hertz. Because the cycle changes every 1 second, so the frequency of the signal is 1 hertz. And take that for different values of the cycle duration, and the actual frequency can be calculated very easily, which is actually 1 over the time. So you can inverse that and it becomes the frequency. Based on experience, students usually get confused between the units. So pay careful attention to the units here. So when I say second or millisecond, so this is actually 1 millisecond. So this is 1 microsecond. 1 microsecond, bro. And this is 1 nanosecond, so on. Okay? Okay, so for the frequency or for the cycle duration, again, we use the power at home as an example. So when we say that the actual power at home has a frequency of 60 hertz, what does that mean? This means that the cycle duration of the sine wave that represents the power signal at home is simply 1 over 60. ماشي؟ 1 over 60 seconds. Okay? If I want to represent it using milliseconds, it would be 1000 over 60 millisecond. صح? So by simple division, this is actually 16.6 milliseconds. Okay. So the period of a signal, if the period of the signal, which is the reverse example, if the period of the signal is 100 milliseconds, so the frequency is 1 over t, and t here, remember that t is 100 millisecond, which is 0.1 second. So the frequency in hertz is 1 over 0.1, which is 10 hertz. Okay? And again, this is a very simple example, and this is valid for a simple sine wave or a simple cosine wave. So you can actually calculate the frequency as the inverse of the cycle duration very easily. So frequency is the rate that the signal change. Is the rate for the signal to change. This is the practical meaning of frequency with respect to time, of course. So if the signal changes in a very short period, this means that the signal has a high frequency. Bravo. If the signal changes in a very large period or a very large cycle duration, this means that it has low value. There are two extremes here. If the signal does not change at all, what is the frequency? Zero. Bravo. Yes, excellent. So if the signal does not change at all, which means like DC voltage, DC voltage, it has constant value. So the frequency of DC is 0. Okay? The other extreme, if the signal changes in 0 time, what is the example of this? Any digital signal. So if you look at any digital signal, the signal takes one value and then it changes to another value in no time. What is the frequency of this? Infinity. Bravo. This is excellent. So if the signal changes in no time, this means that you have infinite. It's written here. Okay. That's why. Okay. So if the signal changes, but at least then she understood what's written, which is good, yeah. So if the signal changes in no time, which means that the cycle of the signal is 0. So 1 over 0 is infinite. So if the signal changes in no time, this means that, and that's why we said that a digital signal usually has infinite frequency. And that's why it's, as we will see later, it's not easy to represent digital signal using actual periodic analog signal. And we will see how to do that. We have to use some approximation. In reality, to have a signal generator that generates a signal like this, it's actually almost impossible. So in actual life, a signal generator cannot really generate a signal that changes its value in 0 time. And that's why, in reality, the actual signal that you can generate in reality is something like this. So you cannot actually have a signal generated that changes its value in 0 time. Okay? Any question? Okay. The third component is the phase. And as we said, the phase is the actual offset that the signal takes from the start value of the signal. So when we say sine, the sine of x, if x is 0, sine is 0, right? So sine starts from 0. So if we find the 0 value at time 0, this means that the sine wave here has a phase or an offset of 0. Okay? The phase is measured using either degrees or radian. So degrees range from 0 to 360. So we have 0 degrees, we have 360 degrees. Okay? Radian starts from 0 to 2 pi, where pi is almost 3.14, something like this, 3.14. Okay? So phase describes the position of the waveform relative to the 0 time. So this sine wave, for example, is shifted left, or in other words, the zero axis has been shifted right, whatever is easier for you, okay, by 1/4 of a cycle. Okay, 1/4 of a cycle. A cycle here, we represent it in radian using a 2 pi. So this is shifted left by 2 pi over 4, or pi over 2, or in degrees it would be a 90 degrees. So this this signal is shifted by 90 degrees, or shifted by pi over 2. Okay? This signal here is shifted by a half the cycle, or pi, or 180 degrees. Okay? And pay attention to the fact that if the signal is shifted left, or in other words, this axis is shifted to the right, this means that the phase is positive. Yani if I start a sine wave, so the sine wave, if it starts from like this means that this has a positive 90 degree, a positive 180 degrees. Okay? If the shift is to if the shift is to the right, then the phase is negative. That's why for some of you, if you understand using shifting the axis, the y-axis is shifted to the right. So this means that the phase is positive. The y-axis shifted to the left, meaning that the phase is negative. So whatever you feel comfortable with, but don't get confused. Okay? Okay, so a very simple example. A sine wave is offset 1/6 of a cycle. 1/6 of a cycle is basically 2 pi over 6. So, or 360 over 6, which is a 60 degrees. Okay? In radian, it would be 2 pi over 6, which is pi over 3, which is around pi. Pi is like around 3.145, something like this, over 3. So it would be 1.046. Okay? Any confusion here? Very simple example. Anyone not following? Okay. The last thing is what we call a wavelength. A wavelength and a period. Here, the wavelength, many people, they confuse the wavelength with the frequency of the signal. A wavelength is actually the distance, measures a distance that the signal travels, okay, over one cycle of the signal, which means that the signal travels through the air or through any medium, right? It actually has to travel with a specific speed. Okay? So what is the actual distance that the signal itself travels between this point and the end of the cycle, between this point and this point. Okay? Some people confuse this with the frequency because they think that the frequency is simply 1 over t and that's it. The difference between the frequency and the wavelength is that a wavelength measures the distance that the signal travels. So there is a propagation speed. In the case of the wavelength, the signal travels with a specific propagation speed. Like if I move from this point to another point with a specific speed, I can calculate the distance that I travel.
So the x-axis is not time, it's the distance?
The x-axis, no, the x-axis here is still the time, but the wavelength itself is the distance, which means that it's time multiplied by speed, right? Yeah, it's why time here? Because I have to calculate the time between this and this, between this point and this point. But the wavelength is not the time. The wavelength is when I go with a specific speed. So the time of the cycle is t, right? The time of the cycle is t. So how much distance the signal travels for a time t. That's what wavelength is. Okay? So how much distance? So if a signal has a cycle duration of capital T, let's say capital T is 10 seconds. Okay? This means that wavelength is how much distance that the signal will travel within 10 seconds. That's what wavelength means. Okay? So this really depends on the speed that the signal uses to travel, to propagate. Right? And that in reality depends on the actual medium. Because if the signal travels through a vacuum, through the air with actually no particles or something, then the signal can travel using the speed of light. But in actual medium, the signal is actually slightly less than the speed of light. Okay? So basically, the wavelength, or we usually use this symbol for the lambda, for the wavelength. The wavelength is actually a distance, which means that it's a speed multiplied by the time or the cycle. Okay? And we know that the time is actually 1 over the frequency. So the wavelength is actually c divided by the frequency. So that's the difference between frequency and a wavelength. Wavelength is actually a distance. It's not a frequency, it's not a time, it's a distance. Okay? But the distance that the signal travels for a duration of time equals to the cycle of the signal. Okay?
What is the unit of the wavelength?
Meter. Distance. Okay? So we can use meter, millimeter, something like that. It's a distance, and it's measured using a meter. Okay? So any confusion? So this is the wavelength. So so now we can discuss briefly the time domain and frequency domain plots. So this is very important to know that if I have periodic, analog, simple signal, this is what we mentioned at the beginning, that the frequency of this signal can be simply calculated based on 1 over the time duration. And why we say that is because when we represent the signal in the frequency domain, okay, because usually the signal is represented in the time domain, which means that you have time and you have peak value. Right? Then people have started to talk about the frequency representation. Why? Because frequency representation is easier to deal with in communication systems. That's why we use filters. Filters are like frequency-based devices. Okay? So a periodic analog signal like this has one frequency, which is one sample in the frequency domain. So this is much simpler, right? So instead of drawing the analog periodic signal like this, which takes different values at different times, in the frequency domain it becomes really a very simple sample at the frequency, which is calculated based on 1 over t, and the value is the actual peak of the value. So instead of dealing with periodic analog signal which changes over time to infinity, in frequency domain, what we need to do is simply to have one sample at the frequency of the signal. And that's why we said that sine wave or cosine wave are actually simple analog periodic signals. Why? Because these are the simplest representation. They have only one frequency component in the frequency domain. Okay? But as we will see later, any other composite signal, they have more than one value. They have more than one value in the frequency domain. And that's why we call it composite signals, composite periodic signals. Okay? Any questions? Okay. So a complete sine wave in the time domain can be represented by one single spike in the frequency domain. And this is the simplest way of representing the sine wave. We represent it using one sample in the frequency domain at the value of the frequency. That's it. So the frequency domain is more compact and useful. More compact, yani it's a simpler representation of the sine wave. So instead of writing the sine wave like this, so it's actually one compact, one simple representation of the sine wave, using one sample in the frequency domain. So if I want to represent multiple sine wave, all I need to do is just to put samples at the frequency of these sine waves. And I can represent multiple sine waves using a frequency domain. Very easily. So it's very useful when we start dealing with more than one sine wave. And that's the actual representation in communication systems, because usually the actual data that we use, as we will see, they are represented using multiple components of a sine and cosine waves, not just one component. Okay? So as we will see in the figure, if you have composite signals, you can represent these composite signals. So these are three different sine waves. These are three different sine waves. Is this a sine wave? This is with frequency of 0, but it has a peak value, right? So it's a sine wave with frequency 0. So we can represent it at the 0 frequency with a peak value of 15. Okay? And the red one is another sine wave. And which one has higher frequency? The one that changes more in a shorter time. So the green one has higher frequency. صح? And the green one has a lower value versus the red one. So the red one has less frequency and higher peak value. So these three sine waves can be represented in a very compact way using frequency domain, as we can see here. Right? So that's why the frequency domain representation, in many cases, in many communication systems, is a very simple and useful way of representing periodic analog signals. Okay? So, in reality, I can, if I generate those three sine waves and then sum them up, it becomes a composite signal. And the periodic signal, if you sum multiple periodic signals, the result would be another periodic signal. Okay? So, but it's not a simple periodic signal, it's a composite periodic signal, similar to the ones that we have shown you before. Any questions? So, a single frequency sine wave is not useful in data communications, and usually we need more than one sine wave to represent any actual signal, and we will talk about that, of course, later. So we need to send composite signals in nature. So in many cases we need to send composite signals, and that's why we started to talk about frequency domain, because frequency domain analysis is usually very, very useful to represent composite signals. The time domain analysis becomes very, very complicated. But in frequency domain, you can use one or two or three very distinct samples to represent composite signals. And to deal with that, it's much, much easier. Okay? So we'll stop at this point, and because Fourier analysis is more complicated.